Hey everyone. So we're going to go through a little scenario here that is going to kind of give you an idea here of how your weight can change um, while at rest or accelerating up or down in an elevator. And we're going to compare the weight of a person here in three different scenarios on an elevator. So in the first scenario here, the person standing on a scale is at rest. Now to do a little simple free body sketch here, we're going to look at a couple forces. One, we have the force of the person standing here, and that force is going to be their weight, or F sub g. Now this is balanced according to Newton's third law with an opposite but equal reaction force. And this is called the normal force. It's always the reactive force according to Newton's third law, and we call it the normal force. So the person in this scenario is applying their weight down onto the scale, and the scale, according to Newton's third law, is applying a force back up onto the person. And right now at rest, the weight of the person is equal to the normal force. So to give you an idea here, if we were to consider the weight of that person, we know that it's the mass of that person times the acceleration due to gravity, or g. Let's call that person 10 kilograms, and the acceleration due to gravity is 9.81 meters per second squared. So the weight of this person at rest would be 98.1 newtons, which makes our normal force, since this is equal, also 98.1 newtons. Now, as far as what the scale is going to read, the scale is going to read the normal force. So whatever a normal force is, that's what the scale is going to read. So right now, since they're balanced and they equal each other, the reading on the scale is going to be what our actual weight is, because the elevator is at rest. The only force in play here is the acceleration downwards on the elevator, on the scale, on the person, due to gravity. In the second scenario, we're going to consider the elevator accelerating upwards from the base floor up to, let's call it the 10th floor. And it's going to accelerate upwards at a rate of 3 meters per second squared. Now, in thinking about this, the elevator, sitting as it was before, was already balancing the weight of the person with the normal force. But if we want to try and accelerate the elevator, the scale, the person upwards, we're going to have to increase that force. So we need an increased force that's required to accelerate the person, which means that normal force has to be greater than the weight of the person. And with some other math aside here, the equation that's going to allow us to evaluate that is if we were to try and determine what the normal force was, we'd want to consider all of the accelerating forces in the y direction, and that's going to be acceleration due to gravity plus any other acceleration that we have in the y. And again, this follows Newton's second law, force equals mass times acceleration. Now, since we have acceleration in the upward direction, this is going to essentially increase our rate of acceleration. So if we were to try and find the weight of the person as we try and accelerate upwards. So we'd have the same 10 kilogram person multiplied times the acceleration due to gravity plus our acceleration upwards. This gives us a new weight. So this would be 10 kilograms times 12.81 meters per second squared. And we get a weight of 128.1 newtons. Now this is more than what we saw in the example at rest, and that's showing us that our normal force here, in order to accelerate this person upwards, has to be greater than it was at rest. So that force vector is going to increase. Considering the third scenario here, if we are going to accelerate downwards at a rate of 4 meters per second squared, if you kind of think about it, it's almost like the scale is falling out from underneath the person as they fall, but the person's not floating in the middle of the elevator. So they're still attached, but it's kind of just falling out from underneath them ever so slightly. So we can expect our normal force here, since it doesn't have to lift that extra person and it doesn't have to hold on to them since you're accelerating downwards, this normal force should decrease compared to the initial scenario. So the normal force should be less than the weight. And that's because there's less force required to accelerate the person downward, which is going along with the force due to gravity. So if we use that equation that we had talked about up front here, or up top here, and we try and solve for the weight of the person again, now that I'm looking at this, this should be f of n. I changed that up there. I have to change that. F of n here, our mass still stays the same, 10 kilograms. But now we have 9.81 meters per second squared. And we have an acceleration in the opposite direction. So we're going to add a minus 4 meters per second squared, which will cause us to subtract that away. I'm going to do this right now. This should not be Fg, this should be Fn. This becomes 10 kilograms times 5.81 meters per second squared, which gives us a normal force of 58.1 newtons. So we can see that with the acceleration downwards, we're going to require a smaller force being applied up by that scale, and it's going to give us a lower reading. Accelerating in the upward direction, it's going to require greater force, and that's going to give us a larger reading on the scale in order to accelerate the weight of the person upwards. Balance that there. And at rest, our normal force is going to equal our weight, as those forces are in equilibrium, since neither are moving in either direction. If you have questions on any of this, make sure you bring them up in class tomorrow. Have a great day.